Good afternoon. Today, let's finish up um about the power limited sources, like real life sources. And so, it's okay. So we had talked about current sources, voltage sources, and then the maximum power transfer theorem, finding max power. All right. So the approach to finding max power is if we have a source and we connect a load resistor to it, noted by RL, we can find power RL. Power can be given as the current flowing through it, I squared times R, and then IL is the total current that flows in the circuit, voltage source divided by the two resistors, RS plus RL. So when you put these two equations together, we obtain power in the load as V square or Vs square times RL or RS plus RL the whole square. Okay. So now let's take the terms outside. And so we can get Vs square and RS square together. So we're trying to find the maximum power. So we want to find the relationship between RL and RS. What value of RL compared to RS gives us the maximum power. So we take that separate out, RL over RS. Note it as X or label it as X. And we can vary the value for RL from 0 to infinity, right? We vary the value for RL from 0 to infinity, figure out or note or observe where we obtain max power or what value of RL do we obtain max power. So if we said X is equal to 0, power turns out to be 0. If we said X is equal to infinity, power again turns out to be 0. So that means maximum power, or the power that appears in the load, is somewhere in between. It's not at 0, not at infinity. And so the person who did some of the original work for maximum power transfer is Morris von Jacobi. And the equation that maximum power transferred when the value for RL is exactly equal to the value of that source resistance. And then max power that's transferred is 1/4 of Vs square or RS. Okay. And this again is known as the maximum power transfer theorem. The law of maximum power. Okay, law of maximum power. This again is an important concept. We do not always want maximum power to be transferred. Sometimes we want power to be transferred efficiently, especially if we are using, let's say, any kind of mobile device, electric vehicle, for instance, where our power or energy storage capability or capacity is finite. And so we do not always want to expend all of that energy, meaning we do not always want maximum power to be transferred out of that battery. We want efficiency also, right? So real life example would be, let's say you have a electric vehicle, right? You have a fully charged battery inside the electric vehicle, and you have two options. You can actually speed or you can go and try and preserve your battery for as long as it. So you can go either mileage or you can go speed, right? So if you want to reach as quickly as you can between any 2 points, you're flooring the accelerator, applying maximum power as much as you want from the battery. And that pulls in maximum power that's transferred from the battery itself, but it's going to get consumed faster. So it's never at maximum efficiency. If you do maximum efficiency, meaning the energy that is stored inside your source, in this case, the battery, is transferred with the minimum amount of losses to the electric motor. Okay, so the heat losses and the mechanical losses that occur are kept at a minimum. So maximum power does not equal maximum efficiency. Okay, that's another key point to remember. Okay, maximum power does not equal maximum efficiency. At maximum efficiency, only a fraction of the power is transferred from the source to the load. Okay. All right. So we talked about voltage sources and current sources. We're going to equate the two and see how we can transform back and forth. So let's say we have a source. That source is a sealed box to us. One illustration of a source is a voltage source. And so here you have a voltage source in series with a resistor. Now it has open terminals here and here. This internal source resistance is labeled RS and is going to drop some voltage across it. And so instead of Vs being available at the output, we have V, just noted by lowercase v. So if you look at this graph here, we have a illustration of how the output voltage V versus as a function of the total current I. Total current I is the current that's coming from the voltage source Vs. So a resistor is linear, of course. So a linear resistor is going to pass through the origin. If there is no voltage across the resistor, there's no current. If there's no current flowing through the resistor, there's no voltage. Right? So it passes through the origin. It's a linear resistor, which has a linear relationship between the voltage and current. So as the voltage or current increases, then the other quantity must increase or decrease at the same rate. Okay, it's directly proportional. However, if we take the voltage V at the output terminals of the source, we can model it as a resistor voltage plus Vs. Right there. So it's shifted up. So the power supply has a linear relationship, except it is shifted up because of the voltage drop across Rs. Okay. So far, so good. If it's a resistor, it is absorbing energy. If it's a source, it's supplying energy. So either the voltage or the current is modeled as negative. Right? For a source, current is always modeled as negative. For a resistor, it is always modeled as positive. So if you have a component in this quadrant, this is the first, second, third, and fourth. In the first and the third quadrant, power is equal to plus VI. Voltage is positive, current is positive. In the third quadrant, power is negative. I mean, voltage is negative, current is negative. Essentially, again, power is positive. So if your component lies in either the first or the third quadrant, then it is receiving energy, it's consuming. But if it's lying in the second or the fourth, then it's a source. because the current is negative or the voltage is negative. Okay, so in the second quadrant, current flows out from the positive terminal. In the fourth quadrant, current flows into the negative terminal. This power is negative. And current I, of course, is modeled as Vs or Rs from Ohm's law. Okay. All right. So as I was saying, the red IV line can be seen as shifting this linear RS curve by a value of Vs. Okay. Vs, of course, ideal source remains constant. Doesn't matter what current we are supplying. So this is for ideal. This is a real or practical. Okay. Real or practical. And then the two electrical models for a linear source is a voltage source and a current source. Voltage source has the resistor in series, current source has the resistor in parallel. Okay, this is a standard representation for a real life non-ideal source. Okay. And of course, we can equate both models together as long as this equation holds true. Ohm's law, V equals IR. Okay, so the total current that's flowing in the circuit, I must be equal to Vs over Rs. So in the next slide, let's take a look at how that is possible. Let's take the two models and short out their terminals. If you take the voltage source and short circuit its terminals, we have current I flowing through the circuit, and the resulting I has a value of Vs over Rs. Okay, make sense? Ohm's law? Yes. Yes, so question being asked is about the short circuit. No, the short circuit is we are actually taking both terminals and just connecting a wire between them. There's nothing else over there, just a wire. And so if we do the same thing with the model of a current source, again, we have current I flowing through it. This time, we can model it as saying that if this current source is passing through here and the short circuit is in parallel to Rs, all of that current is going to flow through that short circuit. The resistance for a short circuit is 0. That's the path of the least resistance. And so always all current will flow through that short circuit. Nothing will flow through Rs. Okay. Even if Rs has a value of 0.1 ohms, technically nothing will flow through Rs. Everything will flow through that short circuit. And so in that case, if I say my source Vs or Rs, and then this IR is equal to 0 because nothing flows through that resistor. And so I get the total current I at the terminals as Vs over Rs, which is the same as we obtained for the first one. Okay. And then if we take both the sources, keep the output terminals open and measure the resistance, measure the voltage at the output terminals, what do we get? V is equal to Vs. Why? Because the terminals are open. Because the terminals are open, there is no current that's flowing through there. If there is no current flowing through there, that means there is no voltage drop across that resistor. If there is no voltage drop across that resistor, it means both ends of the resistor are the exact same potential. So anytime we have open circuit in there, we can apply KVL and we can determine that this quantity goes to 0 and hence voltage V at the output is equal to Vs. This is an important property. Oftentimes you will see circuits where you modify them and you will realize that at the open circuit, meaning the voltage must be the same. And then finally, if we have a current source and we keep the output terminals open, same thing, doesn't have any place else to flow except that resistor. And so the output voltage V is simply Rs times your source, Vs over Rs, which gives us Vs. So if we take these four circuits, we realize that either whether it's open circuit or whether it's short circuit can prove that both the voltage source and the current source are equivalent to each other. I don't know why this keeps happening. Oh, battery test. We'll leave it for next class. Okay. All right. We'll end class here today and we'll pick up again on Wednesday.